parametric equations. We are doing absolutely no calculus today. We are doing the pre-calculus portion of parametric equations. Parametric equations was something that's actually in the pre-calculus curriculum. A lot of times it's skipped because it's not even in Cal 1. And so I made the decision that I'd just do it all at once instead of teaching it and you forgetting it and then me teaching it again. Just teach it all at the same time. Parametric equations are equations with an x and a y component with respect to time. Time is the variable, the independent variable. And you have essentially two dependent variables, an x coordinate and a y coordinate. These will graph pictures that look just like regular functions. The biggest difference is that they have a time component involved. So this becomes really important in things where time is important. For example, if you are an air traffic controller, do you care if two planes pass across? They do all the time, don't they? What do you really care about? When do those two planes pass across? And so this takes into account not only the x and y coordinates, but the time component of that. When a plane is in a certain location. And so that's what parametric equation involves. You can take parametric equations into 3 dimensions by adding a z-axis. So then you have a 3-dimensional space with x, y, and z. We will not do that in Cal 2. That would be Cal 3. So that's what you go on to Cal 3. Practically, you do Cal 2 again. Put a z on the end. But so fill the table of values for x and t. And plot the x and y coordinates on the standard coordinate plane. So I plug -2 into x of t, and what do you get? And what do you get when you plug -2 into y of t? And so I can plot those, and as I plot a parametric function, I am going to lose some information. I'm going to lose the time component. So we're going to designate that with an arrow, so at least we know which way the function was being plotted, because it could be being plotted in multiple ways. Your calculator does take into account the time component. When it plots a parametric function, it will say it plots. So you put 2 different parametric functions in. You know, in function mode, it'll graph the first one and then the second one. In parametric mode, it will graph them simultaneously, and you can see where the end is at. So it's kind of neat how your calculator will work with that. So at time -2, I'm at the position -1, -11. Change it. -1, I was at 1, -7. 3, -3. Now, what you notice is graphically, I lose all the aspect of time because I take a moving graph and put it on a stationary picture. So I lose the time element once I put it down. does appear that it's still linear. Does everyone agree? And so as I draw this, I think it's linear. Does it look linear on the calculator? I'm going to put arrows that indicate which way that graph was going. It could have started at the right and gone down because of the time element. So it gives us a direction. Much like a vector, which you'll see a lot of correlations between vectors and parametric functions. Yes. So the only thing I can plot the x and y, I cannot plot the time coordinate. So what I actually get is a function mode picture from two parametric equations. So you can always find the rectangular coordinates for a parametric set of equations. Again, you lose the time component. Time component's important, but sometimes you just want to know what the path looks like. So that's a parametric equation graph. Then I asked you a challenge question. See if you can write the rectangular coordinates for that set of parametric equations. So that's the theory. How did you get that?
So I know the slope is 2, and then I just set one of the points equal variables, and I see it's on.
Does everyone agree that seems like it should work? Now, obviously not everything's going to be linear, so we wouldn't want to rely on that option. So I'm going to show you another way to find the rectangular coordinates. I'm going to write the top equation as x equals 2t plus 3. And the bottom equation is y equals 4t minus 3. I just didn't write the up t part. I'm not saying no, that it couldn't work. Probably more work than it needs to be. With a little bit of substitution, though, you can do what's called eliminating a parameter, or getting rid of a variable. Getting rid of the variable t allows us to see the rectangular coordinates. Now, sometimes we will want the t when we want it at a time. Other times we just want to know what the path looks like. In which case, rectangular coordinates is more feasible. So you can eliminate a parameter and put it in rectangular coordinates. To do that, I'm going to use substitution. You can use either of the two equations. Subtract 3. So x minus 3 over 2 equals t. Does everyone agree? I did that fast, but subtract the 3, divide by 2. I can substitute that in. To simplify, y'all okay with me doing 4 divided by 2 is 2. So I get 2x minus 6 minus 3. I think Joseph's guess was right. It was more than a guess. It was a very educated guess. But to get there, you had to plot a lot of points to see that it was linear. This way, this way. Pretty quick substitution. So that's how you convert from parametric to rectangular. Now, to go from rectangular to parametric is not done as often because you don't know the time element. So it can be done. The easiest way to do it is just to say x equals t, and then go from there. But you could redefine it infinitely many ways. Parametric. So this is the way that's works. So parametric equations are useful in modeling motion because in addition to horizontal and vertical distances, they include a third variable how much in its path, but at what time it is square, things like that. So that's where parametric equations are important. Other than that, they are not too terrible to work with. They just have a time component. And much like a vector, which we will talk about next week, they have a horizontal component and a vertical component and an x and y component with respect to time. Is it cold in here? Okay. It's rare for me to feel especially upbeat. So before we do an application problem with parametric, I just want to do another one like the bell ringer. This is what your homework mainly looks like tonight. Just getting you familiar with parametric equations. We could spend weeks on them in pre-cal, but they're never real difficult. There's a lot of different applications that we could expose you to. Tomorrow, well, maybe tomorrow we'll see where we get. Tomorrow or the next day, we'll start looking at the calculus. So this asks us to make a table of values and sketch the curve indicating the direction of your graph, and then eliminate a parameter. I'm going to pick some values with some negative t's and positive t's. Some teachers will only ever have you do positive t values because of time. So take that as you will. Depends on what you're doing. Probably in the real world you would always start with t equals 0. So if you wanted to do that, that's fine with me. Let's start by making a table of values. For this particular problem, can I use negative t vectors? Why not? The x value is not defined, is it? So that's not going to give us a point. Which in real world time makes sense. X at 0 would be 0. Y at 0 would be negative 2. X at 1 would be 1. 2, 0, 3, 1. Now, if I were plotting these points, I would probably plot just the ones that made whole numbers, maybe the x-intercept and y-intercept as well, but so at 0, I'm at the x value 0, y value -2. At time 1, I'm at the x value 1, y value -1. At time 2, I'm at the square root of 2, 0, which is somewhere between 1 and 2, 1.4. So if you want to plot that one, you can. It does say don't use a calculator, so if you didn't want to plot that one, it would be okay. I'm going to skip down to the 2, 2. What kind of graph does that look like? Looks like a parabola. Looks like a right-hand side of a parabola. And I'm going to draw it with direction arrows on it. So know which way I'm going. So Sometimes they will tell you what time to plot it between. Like if they said plot it from time 0 to time 10, you would stop when it told you to stop. And this one didn't give us the information. Okay, any questions about the table of values and the sketch? Eliminate a parameter. How would I do that? Easiest way to do that would be to square the x. And so y would then be, does that appear to look like x squared minus 2? That's parametric equations. One of the most common applications of parametric equations is projectile motion. You know that equation you have to memorize for projectile motion in rectangular coordinates. The gravity constant t squared minus plus the initial velocity times okay. There's one of those for parametric. The good thing about this one is I don't think you need to memorize it for basic calculus exam. So it's not going to be one of the things you have to memorize. But it is something that you need to be aware that exists. And you could Google it and look it up if you are in a upper level calculus class. Parametric equations to model projectile motion for x and y in parametric mode, where h is the starting distance from the ground, g is the acceleration due to gravity, and v is the initial velocity, are those equations. Why do you think they involve trig functions? Would the angle at which I shoot a projectile up affect where it goes? Makes sense, right? Why is there no gravity constant on the x component? Gravity does not affect the horizontal distance. What does gravity affect? It's the vertical distance. And you can imagine x has something to do with cosine of theta, because remember from our unit circle, x is very much affected by cosine. And then the y is the velocity times sine of theta minus the gravity, acceleration due to gravity constant, and then plus the initial height. So y has more things factoring into it. It has the normal trig component that would just give you a normal y value, but then it has the subtraction from gravity, but the addition from whatever initial height you started at. So that's where those equations come from. A batter at spring training camp hits a baseball with initial velocity of 90 feet per second at an angle of 35 degrees from the horizontal. Assume the batter hits the ball at 2.5 feet above home plate. What value for gravity would you use in this problem? Why? Feet. We'll shortcut that explanation. We're in feet, so we're going to use gravity constant. Write a parametric equation, a set of parametric equations to model the motion of the ball. So I'm just going to use that information. The initial velocity, which is 90, cosine of 35 degrees. So that will give us the horizontal component of the ball, the vertical component of the ball would be 90t sine of 35. I did have to memorize this equation in my calculus class. It's not as scary as it looks at first glance. If you think of it as horizontal component and then vertical component minus the gravity constant. And as you know, even from the equation you learned in AB calculus, the negative 1/2 times the 32 gives us negative 16 t squared. So that should look familiar to you, that negative 16 t squared plus 2.5. The first question they ask us if we could use calculus or not to do this question. We could either just use our calculator and non-calculus, or we could use calculus without a calculator. What is the maximum height reached by the ball? What is not a question in there? What's the distance? So to answer question 3, would I have to consider the x component at all? No, I would just need the maximum y value. So I could either find out with calculus by doing derivatives that equal to 0. You would find the t value. You wouldn't want the t, but what would you do once you find the t? Plug it back in. So we can find this with calculus pretty easily. Remember, sine 35 is just a constant. It's a weird number, but it's just a number. Or we could plug that in our calculator and find the maximum. Since today is pre-cal, if you want to do it that way, that's fine. You can imagine in calculus, we will do that with calculus. But I don't have to consider the x component at all. I don't have to have my calculator in parametric mode to do this, do I? And I just plug that in, the x instead of t, find the maximum height. So there are a couple ways you could do it. I think I'm going to use calculus just for fun. Y prime would be 90 sine of 35 minus 32t, right? Everyone agree? So t would be 9 sine of 35 divided by 32. Everyone agree? 90, that's definitely right. Thanks. And then, so that's the time at which the ball is a maximum, right? Everyone agree? So how would I find the maximum height? Plug that into y of t. So someone with a calculator do that for me. $1.490 is the y value. Oh, yeah, but I don't know the y value. How did I know that wasn't the y value? It was, yeah, the maximum height of the ball started at 2.5 feet. It's going to be more than 1. What was your question, Walker? How fast what? You sure? We might answer. And when he hits it, he hits it at initial velocity at 90 feet per second. No, that's how fast the ball comes off the mat. Yeah.
Whenever it just says eliminate one of that means right?
Get rid of the T. Okay. What is the horizontal distance traveled by the ball? How could we find that? Good. When y equals 0, why would that give you, why could that help us find the horizontal distance? That tells us when the ball hits the ground. That'll tell us the time at which the ball hits the ground. Could we use that to find the horizontal distance we traveled? Okay, so I agree. I like that plan. Yeah, I suppose the way it's worded, because you have from this you'll have no way to know how far it was. So it must be muddy. Okay, so I'm going to take a y, and you are welcome to use a calculator and set that equal to 0. I would recommend a calculator. You could use polysmalt on this if you wanted to, because 90 sine of 35 is just a constant next to t. Or you could use your regular function mode graphing screen and find the intersection. So pick one of those two things and find this. Or you got a TI-89. You could use your solve button. You got options. Polysmalt. In the 89, it's built in somewhere. Polynomial root finder, I think is what it's called. In the 84, if you want to have it and don't, it would take me about a minute. Put it on your calculator. It's handy occasionally. Like I said on the TI-89, you could also just use F2 and use your solve button. So you've got some flexibility. But I do want everyone to solve it somehow. I don't care how you do it, but I want everyone to solve this equation somehow.
We did solve the
Comma, well, it actually doesn't matter. Whatever you do when you set the equation up, you'll do comma that variable. So if you use x, then you'll do comma x. If you use t, you'll do comma t. The calculator, does everyone remember how to get decimal answers in the 89 diamond insert? Because it will probably give you some nasty quadratic formula looking answer at first. Okay, now which one of those will I want to use? The one that's not negative. Why will I want to use the one that's not negative? And what is that?
0.06321.
Okay, make sure you store that or keep it handy. Because I don't want to use the rounded form because I'm not finished with the problem. What am I now going to do with that? What am I now going to do with that value? Plug it into x of t. And what is that? Remember, use the stored version. If at all possible. Well, that's x. So if I put it backwards, doesn't make sense either.
I can't get mine to give me a question.
Diamond and
Oh, yeah, I did that, but then it just gives me something weird.
Yeah, it just is making me
It just like sends in, puts a 125 out front instead of divided by 3.
degrees.
I think so.
I bet you're not.
Oh, just kidding. You gotta go to mode.
Yeah, we all. Why do we have to be in degrees?
How did it get rid?
Yeah, we have to go back.
Okay, yeah, no, it's still good.
Is it still doing that?
Yeah.
It should be 3.27.
Great.
Okay, and then let's try that again. Why do we need degrees again? Someone remind me. Cosine of 35 degrees.
not just because of what you find in
I got 41.371.
Well, I forgot the other day.
You put y equals instead of 0 equals. So it's giving you the of.
Zero equals. Why did you tell me?
Look, it's taking it through there. There's like straight line.
Zero.
Okay.
Because we're taking it as
Just a second, please.
241.378. Now, I would immediately change back to radians. Remember, default to radians. The only time you would need degrees is if they gave you a degree. The only time that's going to happen generally is when they project on most problems. So leave your calculator in radians. Anyway, so this is just an interesting problem.